Surgery went well, so I'm on like 3 hours of sleep right now, so I'm gonna do my best, all right? Pay attention for mistakes. They may happen today. All right, so last class we were talking about slopes of tangent lines. We did several examples, saw how the algebra comes into play. And this was the definition that we were using. This was the limit that we used. And hopefully you're all comfortable with that at this point. And then towards the end of the class I said, all right, well, there's another way we could draw this picture where you kind of label these points a little different than here. And when you do that, your slope of your tangent line is, the formula is going to look a little different. So we have like two versions of the same thing. They both give you the same numerical quantity, which is the slope of the tangent line at that point. So over here, if we calculate this limit, it should give us the slope of that tangent line. And if we do this limit, it would give you the same slope of that tangent line. All right, so they are equivalent in terms of what they produce at the end, but the notation is slightly different. So now that we've got these two limits, we are actually going to start to use some new notation. So instead of me giving you a function and saying, hey, go find the slope of the tangent line at a certain value, I'm just going to write this down. Right there. So it's f with this little prime mark. So the way you would say this is f prime of A. Okay, f prime of A. F prime of A is simply the slope of the tangent line of that function at A. And we call this the derivative of the function f at A. All right? Now, if we change it and we want to look at this other definition here, this other limit, then our notation would be f prime of x. And that would mean the derivative of the function at x. So the main difference is that our base point, in this formula, the base point is A, right? And over here, the base point, we just call it x instead of A. So that's why they look like they're two different things, but they're actually the same value. Does that make sense? Okay. So on your homework, there was a couple of problems towards the end that used this notation. We just hadn't gotten to that yet. So now that you know that, let's do an example just to get kind of warmed up with this. And then we'll move into the next section. Oh, also, the quizzes from last time, if you did not finish those and you want to turn that in, let's go ahead and turn those in now. Anyone else? Okay, thank you. Okay, thank you. All right, so let's do a problem here. We'll just do something kind of straightforward, just to get us warmed up. So let's say we have the function f of x equals 1 over x squared. And we're asked to find this. So you're being asked to find f prime of x, which means we're trying to find the derivative of the function at the value of x. So remember last class we did that one example where I did like, let's do parts A, B, C, D, E, F, and everyone's like, no, that's going to suck, it's going to take forever. And then I said, but if we do it for an arbitrary value, we can get like a formula for this slope. That's what this is saying. It's saying I'm not going to tell you what the base point is. I'm just going to call it x. And what we should generate after we do this limit is a formula that would represent the slope of the tangent line if somebody tells us what our base point is. All right? So I'm just going to go to the formula right here. So this is f prime of x equals limit h approaches 0 Okay, so we need to figure out what f of x plus h is. So what is f of x plus h here? So we're going to take our function, we're going to replace x with x plus h. So we should have 1 over the quantity x plus h squared, right? And then I need to subtract from that f of x, which is just going to be 1 over x squared. And then divide all of that by h. And so what did we do last class when we had these like complex fractions like this? What was kind of the technique? Common denominator, right? So we want to put the two numerator fractions together. So we'll just multiply this top one here on the left by x squared over x squared. And we'll multiply this one here by x plus h squared over x plus h squared. And that should give us a common denominator, right? Okay, so now let's multiply out the top. All right, so x squared times 1 just gives us x squared. And then I'm going to go ahead and do minus. And then 1 times x plus h squared gives me just x plus h squared. That is going to be over what? The common denominator, x squared times x plus h squared. And then all of that with a bigger division bar is over h. Now we know right now that if we let h go to 0, this will turn into a 0 over 0 type limit. So we know we've got to finish cleaning this up, right? And how are we going to clean that up? I mean, eventually we want the h to cancel. So what can I do to start to manipulate this a little bit more? We're going to get some x squareds to cancel, but we first have to expand the x plus h squared, right? We actually have to FOIL that out. So you got to pay very careful attention here to your expanding. I have a minus sign here, right? That minus sign right there is going to impact everything that we get when we expand that. So the expansion of x plus h squared, right, is x squared plus 2xh plus h squared. But then we have to subtract every term. So it should be x squared, what? Minus 2xh and then minus h squared, right? All of that over our common denominator. All of that over h. And I told you last class, if you do it right, you should eventually get to a point where you can see an h, like there's just going to be, every term on the top should just have an h in it so you can factor it out. Do y'all see it? The x squareds are going to cancel. So I'm going to write a little bit more. I know this kind of wastes paper, I guess, if you want to argue that this is showing too many steps, but just clean that up. And now you see that I can pull an h out of both of those. So I'm going to factor the h out now. Still have my common denominator. All still over h. And now we're at a point where those h's can cancel. So this h and this h are gone. So the final result, before we take the limit, right? I still have not taken the limit. Limit h approaches 0, and we get on top negative 2x minus h, and on the bottom we have our common denominator, x squared times x plus h squared. Any questions on that up to that point? Now, what do we do? Let h go to 0, right? So let's see what happens when h goes to 0. When h goes to 0, that goes away, right? And that goes away, you just have like x plus 0. So on the top we have what? On the top, negative 2x. On the bottom we have x squared, right, here, times then whatever this is, but that's x squared again, right? So x squared times x squared, that's x to the 4th. But we actually have an x up top also, right? So we can cancel one of the x's, and we should get negative 2 over x cubed. Okay. So I'm looking for a volunteer. I won't pull these sticks. Looking for a volunteer to explain to all of us what the heck that is. Who wants to? Go ahead.
Is that the derivative, like the equation that you can plug? If you have 1 over anything squared, then you can plug that in for x.
I'm not quite sure I understand you.
So, like if you want to plug in f of x equals 1 over 2 squared,
Okay.
and instead of working the whole problem out, then you have that number, you can plug 2 into negative 2 over 2 cubed.
And that would give us a number, and what would that number mean? Slope, okay. I'll come to you next. We're going to get several explanations here, okay?
So that's the derivative, which is the generic formula for any x coordinate you could possibly have. And then it'll spit out the slope of the tangent line on that function at that specific x coordinate, and then you can use that to substitute into the point slope formula.
To get the equation if you want it.
Entire equation.
Okay, I think that's it. Let me restate kind of it. I'll do it in my own way, but that's exactly right. This is a generic formula we have now. This generic formula will spit out the slope of the tangent line at any value of x that you pick for that particular function. So if you want to know what this function's tangent line, what the slope of it is, let's say at the ordered pair, let's see, what would happen if I plug 2 into that? I get 1/4, right? So that point's on that graph, right? If I want to know what the slope of the tangent line is at that point, all I have to do is take this formula and replace x with 2. And that would give me the slope of the tangent line. Then, of course, from this and that slope, you could create the equation. Did you have another? Or you think we've kind of covered it? Okay. All right. Got it? Now, with that in mind, I want you to think about this. Back in college algebra, we had operations. Hold on, operations. I'm really tired. Operations on functions. All right, so going back to college algebra, if we had 2 functions, we could add them, right? That was the notation to add 2 functions. And then if we wanted to subtract them, you can just put a minus there. If we wanted to multiply 2 functions, right? We do that, right? Then we could divide 2 functions. These were our arithmetic operations. And then with functions, you also had this other thing you could do, composition, right? F of g of x. All of these operations on functions take 2 functions in and then spit out a new function, right? You take 2 functions, you add them, you get a new function. 2 functions multiply, you get a new function, right? 2 functions divide, you get a new function. 2 functions compose, you get a new function. What we have going on right now with this whole derivative idea is something completely different than this. What we're doing is, instead of taking 2 functions in and creating a new function, like here, we're starting with a function f, right? We're doing something to it, and it's spitting out a new function, right? Like, for example, the function we just had was 1 over x squared, right? And then what we did is we did something to it, and it spit out negative 2 over x cubed, right? This function, and these are both functions, right? So we have this new operation that the input is not 2 functions. The input is what? 1 function. And the output is some new function, right? And this operation to get from here to here is called differentiation. Okay, that's the operation. So whenever you have a function that goes in and a function that comes out, then this thing right here is called a functional operator. Now this is beyond what you need to know, okay? I'm doing it because some of you are math majors or want to be math majors. A functional operator is something that takes functions in and spits functions out. A function takes numbers in, spits numbers out, right? Function, number in, number out. A functional operator takes functions in, function out. Understand? Okay. So this whole thing, this functional operator called the derivative or differentiation is what basically the rest of the class is about. We want to be able to start with some arbitrary function that anybody can hand us a function, and we want to be able to send it through this operator and come out with its derivative. All right? If we can do that for any function anyone ever hands us, then we are ready for Cal 2. All right? Got it? Now the process of getting from here to here is not going to be easy all the time. The previous example was pretty straightforward, a little bit of algebra, but the limit was doable, right? Doable. All right, so we are heading to that. So let me do one last example, then we can formally move on to the next section. If you have a function, let's call it f of t, or f of x, gives the position of an object as a function of time, then I'm about to tell you what happens, but I'm going to draw a picture first. Let's say we have a function. This is x. This is our function. This is time. And position we're going to say is distance. Okay, so if you want to look at that position as being distance instead, that's fine. So let's say we have a function where you plug in the time and the function spits out how far you've traveled, all right? Then if I draw this function and pick some point there, the slope of the tangent line would give me what? Go ahead. It would give me the instantaneous speed, right? Velocity. Instantaneous velocity. And the way to think about it is the slope of this tangent line is rise over run, isn't it? And when you take the rise is a distance, and the run is a time, then the derivative of that function at x will be a quantity that gives you distance over time, which by definition is speed. Or in this case, we'll say velocity, but technically speaking, velocity is not the correct terminology because anyone take physics? There's a difference between speed and velocity. So it is going to be speed, but the book that we do, it does call it velocity at this point in the book, all right? So the derivative of a position function will always yield the instantaneous velocity. I'm just going to say instant velocity. Okay. So remember, starting with the function, we do differentiation, we get new function, right? If this is a new function, can I graph it? Yep. Sure, I could graph it. And if I graph this function, here's time, because it's still a function of x, and x is still time, but what's the output? Is the output position anymore? What is it? What's the output of this? Velocity, right? So here with this function f, the input was time, the output was distance. If we take the derivative and we graph it as a function, I'm just going to graph whatever, then time's still the input, but now the output is giving you the velocity at every point in time. So this will be velocity. I'm just gonna put velocity, yes? Okay. Let's call this function something. Let's call it, how about v of x? So in other words, I'm saying that when you take the derivative of that function, you get a new function, f prime of x. But that, let's just call it v, all right, v of x. Well, what could we do with v of x? Could we take the derivative again? We could, couldn't we? I mean, this is a function, right? So if someone hands you a function, we should be able to take its derivative. If I take the derivative of the velocity function, that is going to give me a ratio of what over what? So remember, when we did the derivative here, slope was distance over time is speed. If I take derivative of this, it will give me a ratio of velocity over time, and velocity over time by definition is acceleration. And so this would give us the instant, or the instantaneous acceleration of the object. Does that make sense? So if you're going to take anything away from this, take this away. If you start with a position function, taking the derivative one time will give you the velocity function. Taking the derivative of that function will give you the acceleration function. All right? We'll talk more about that later. It just appears in the book at this point in time. When we get some more formulas, we'll do some applications with that. All right, we're ready to move on to 2.2. 2.2? 2.2. All right, so 2.2 is going to be very visual here at the beginning. All right. I just said that if we start with the function f, right, f of x, that if we take the derivative of it, this is still a new function, right? So this function has a graph, and this function has a graph. What we want to do right now is I want us to look at a specific example of a function. So here it is. See this red one? I would like for us to graph its derivative. Okay? So let's try and do this. Where's my big old yardstick? Is there a big old yardstick in here? No? Not in this room, huh? I'll take it. You just happen to have that. Oh, I thought you pulled it out of your back pocket. Whoa. Okay. All right. So we'll use this. Is okay? All right. So I'm gonna ask. I'm calling some people here. How about Elijah? Is that right, Elijah? Right?
Yes.
Okay. So Elijah, all I want you to do, I'm just going to pick an arbitrary value of x, right there. I'm going to go to my function, and I'm going to draw the tangent line. You agree that looks like the tangent line at that point? Okay. The slope of that tangent line is about like that, right? Is that positive or is that negative?
Positive.
Positive. What would you say it's positive what? About? Just eyeball it. Like rise over one, run. Like 1 over 1? Think it's about 1? Does everyone agree that slope looks like it's about 1? Okay? So at this particular x value, the value of the function is just this dot. But the value of the derivative, you say, is 1. So I'm now going to plot that. So what I know about this function is that at this particular value of x that we're plugging in, let me call it a here. At that particular value, Elijah is saying that at that a, it looks like the derivative is about 1. Yes? So since this is a new function, I'm just going to plot it. At a, it should spit out 1. Right? At a, it spits out 1. All right, let's go on. Jackson. How about here, Jackson? Let's call that B. So the slope of the tangent line, here's the tangent line, you agree? What would you say that that slope is?
I'd say it's probably like,
About.
yeah, like 1.5, almost 2.
Positive or negative?
Negative.
Negative, right? So we have a negative slope. Rise over run, so like down over. Like what does that look like, that ratio? Does that look like 1-to-1 maybe?
Yeah.
Yeah. So down 1 over 1. So would you say that the slope there is -1 about? Okay. So at B, it looks like we have -1. So now I'm going to graph that. At B, I have a dot that I draw. Let's make it -1. And you know what? I'm going to change the colors of this because -1's here. And here we're at +1. What I'm trying to do is graph this, right? Okay, Al, can you tell me somewhere on this graph where the derivative would be 0? So I'm asking you the question backwards. I'm actually asking you, where is the slope of the tangent line 0? So I'm asking there. So at x is 0, does everyone agree that if I go to x is 0 right here, that red point, or that red dot, or that's a black dot. I'm tired. Okay, that the slope of the tangent line, I would be like this, right? I'd be flat, and flat lines have slopes of 0, right? So that means that if I graph this purple function, I need to put a dot at 0. Yes? Okay. Let's see. Ian? Ian? Ian, okay. All right, Ian, can you tell me anywhere else on this graph where the slope of the tangent line would be 0?
Let's say down at the bottom.
Down at the bottom, right? Right here. At that point right there, the slope of the tangent line would be 0. Which means when I graph my purple function there, right, when I go to this x value, I'm going to put a dot right here. Yes? There's another one here, isn't there? And that means I'd have to have a 0 here. All right. What about right here? Slope of tangent line there. Positive or negative? Positive, right? I don't know, we could argue about what the slope is, but it is positive, right? So maybe about here, put another dot somewhere up here. What about right here? Is that slope positive or negative? Positive, but it's not that steep, is it? It's a pretty shallow slope. So it's a positive number, but it's a small positive number. So what we have up here is a small positive number. Are y'all kind of seeing what's going to happen here? If I go here, slope of tangent line still positive, but small. And if you look at everything between here, what you get is, this a little off, is it looks like our derivative would do something like this, doesn't it? It's supposed to go through. You all see that? And then on the other side, picking points and doing tangent lines same way, you would see that it goes like that. So the purple function is the graph of the derivative of the red function. Now, in my experience teaching this, you either see this or you don't, and it's like a light bulb. When the light bulb goes off, it goes off and everything's good. But until it goes off, it's like, what the hell is he doing up there? So I have another example, all right, for us to look at. Yes? Okay. Let me see if this next one. All right. So what about that one right there? That's a line, right? Yeah. What does its derivative look like? So if I go to some arbitrary point on this function right here, the slope of that would be something, right? Would it be positive or negative?
Positive.
Positive. Let's say, I don't know, like positive 3 maybe. I kind of gave it away with this, but the slope of that line is 3. So I would go out here, I would plot a point at 3. Now what if I go to this x value here? What's the slope of the tangent line there? It's also 3. So I put a point right here. What if I go here to that point? What's the slope? 3. And so I put 3 there. And wouldn't it be 3 everywhere? So the derivative of this function should just be a horizontal line, because your slope is always constant on that line. Does that make sense? Okay, let's do a different one. How about at 0? What's the slope of the tangent line at x equals 0? Okay, so slope here is 0. So that means I'm going to plot a point at 0. All right, what about, I don't know, right about in here? What's the slope of the tangent line there? Positive 1 maybe, or 2, I don't know. But it's up here somewhere, right? What about if I pick a point over here and go up like that? What's the slope of the tangent line there? It's going to be steeper, isn't it? Steeper than here. Steeper. Which means it's a bigger value. Which means it's going to go up like that. Now what about on this side? If I pick a point here, plug it in, slope of the tangent line there? Negative number. Go over here, way up there, slope of tangent line? Negative, but big negative, because it's very steep, isn't it? So big negative number. And then if you connect those together, that would be your derivative. Let's try another one. This one I'm going to draw myself. So here's the function. 1, 1, 2, negative 1, negative 2. All right, so here's the function. Here's what it does. It starts here, goes up to here, goes down to here, goes up to here. That's your function f. What does its derivative look like? What can you tell me about the derivative everywhere between here and here? It's always the same slope, right? So what is the slope of this line? You can tell because I included the point. So rise is what? 1 and run is 2. So the value should be, what's that slope? 1/2, right? 1/2. So here's 1/2. And so at every point in here, I would go up 1/2, 1/2, 1/2. And I get a straight line like this until I get to the end there. Now, what about between here and here? This little line segment, the slope is always the same, right? The slope is always what? 1. Negative 1, sorry. Negative 1, right? So that means my derivative should be down here at negative 1. I should be able to draw a little horizontal line like this. Okay? And then what about between 1 and 2? It's positive, but you can actually tell the slope is what? Up 1 over 1? So I should draw my graph like this, up at 1, right? So check out that derivative. It's weird looking, right? It's like this, and then all of a sudden it's this, and then all of a sudden it's that. Now, you might be asking yourself, what happens at 0? What's the derivative at 0? Well, you're up here at 0, you're up at this corner, aren't you? And so we start to have our first issue when it comes to derivatives. Remember, the derivative is a limit, isn't it? And remember, limits sometimes don't exist. So what would be the derivative, if I'm trying to figure out what's happening at 0, what would be the derivative as I come in from the left? 1/2. What's the derivative as I come in from the right? Negative 1. And so I get two different values, don't I? And that means that at 0, the limit does not exist. And it's because you have a sharp corner there. It's not like a parabola. It's not rounded over. So we're going to put an open circle here, and here an open circle. What about at 1? Same thing, right? We have this corner. And because we have a corner, we're going to have open circle here, open circle here. Now, to really try and to stress to you why we have problems at corners, just take a look at these two again. All right, you just tell me when I put this up here, I'm going to be moving along the curve. All I want you to be thinking is the derivative positive or negative, and is it big or is it small? All right? So here, what? Positive, big. Positive, small. Positive, smaller. Positive, smaller. 0, then negative, small. Negatives, bigger. Negative, bigger. Negative, bigger. Negative, bigger, right? So it's like a smooth transition. The derivative goes from big positive number, smaller positive, through 0, then to negatives, then bigger negatives. So it's like this nice smooth transition, yes? Here, what happens? What's the slope here? Positive, and it's just fixed, isn't it? Positive, 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 positive. Then all of a sudden, right? Negative, 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 negative. It's not a smooth transition, right? It's at the corner, your derivative goes from positive number to a negative number, and it doesn't transition through all the numbers in between. And when you have that happen, then our derivative will not exist. And there's two other types of problems we can have when it comes to derivatives. So when do functions fail to be differentiable? When is it that you cannot take the derivative of a function? There are 3 different cases. Anytime you have a corner or a cusp, anytime there's a jump in the graph, or anytime there's a vertical tangent. Now I have visual representations of this. Okay, so there's an example of a corner. If I show you what the derivative is, so if I'm moving at a point, right, and I'm graphing the derivative is being held constant, right? And then what happens when I get to the corner here? Boom, all of a sudden it jumps, right? So at the corner, our derivative jumps. So anywhere where our function has a corner, we don't have a derivative existing there. Anywhere where our graph is our original function has a jump, then we won't have a derivative. So here you can see again, if I show you what's happening to the derivative. Whoa. Okay, so my derivative right now are positive numbers, right? My derivatives are positive numbers. And then all of a sudden, I'm going to get to this jump, and then what happens? They switch to negative. So it's kind of like the corner, but anytime you have a jump in the graph, your derivative will not exist there. And then vertical tangents. So check out this function, and check out what happens as I try and graph the derivative. Small positive numbers, right? Small positive, small positive. Now what's going to start happening to the derivative as I move closer? Positive numbers, but bigger, 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 bigger. And then what happens when I get to 0? I get a vertical line, right? I get a vertical line. And the problem with that is, what's the slope of a vertical line? It's undefined. And therefore, how can you talk about the derivative? Because the derivative is supposed to give you the slope of the tangent line. And if the slope is undefined, then the derivative cannot exist. So anywhere where you see a vertical tangent like this, your derivative won't exist. So corners or cusps. This is a cusp. Corner is like sharp V. Cusp is more like 2 U's coming together. Cusp, corner. All right, I need to scroll back up in the notes here. Now, some more notation. some more notation. Here, I think that's all I need. You can put that back in your pocket. All right, so as you move on in calculus, you'll see that we use all sorts of different notation to represent the same thing. So I've already shown you that if y is a function of x, okay, so y is some function of x, some curve, then this is what we started class with. This means the derivative of the function at x. This is the slope of the tangent line at x. Now, if somebody writes y prime instead, they mean the same thing. All right, so that's the same notation. If somebody writes dy dx, they mean go find the derivative. If they write df over dx, they mean go find the derivative of the function f. X is your input, like your independent variable. Or you'll see d dx of the function. So this just means take the derivative of the function f, treating x as your independent variable. This one, capital D of f of x, means take the derivative of f, right? And then this means take the derivative of f, treating x as your input variable. So that's kind of like, why do we have so many notations, right? Well, because like if you take Cal 3, you're going to realize that there are functions that take more than one input, like that. Like a function that takes in, instead of just taking in one number, it might take in 3 numbers. And so maybe it spits out like x squared plus yz. So you give me an x, y, z, I'll give you an output. And maybe I want to know something about a slope of a tangent line. So if I just write f prime like that, that's not enough. I need to give you more information. So what we use is something like this instead. Because that tells you take the derivative, this time treating z as the input of the function f. Don't get too bogged down on this, all right? The main notations we're going to see here are these 3 right there. All right, those are the ones we're going to see mostly in this class. And then also, you'll see this one. This one I don't think I'll ever use. And this one I won't use. And this one I won't use at all. Now in Cal 3 or something, you'll see those again. All right, so whenever we see this notation, dy dx, this is called Leibniz notation. And I told you on the beginning of class that there are 2 people who came up with calculus, Newton and Leibniz. Leibniz, and they did it independently. I said that, right? They figured it. They developed calculus on their own. Didn't know that each other even existed. And so Leibniz used this notation to talk about the derivative, and Newton used more of like the prime notation. All right? Now, we just talked about, when a function has problems with the derivative, right? So when you say a function is differentiable, when we say a function is differentiable at a, it just means that the derivative exists. The derivative is a limit. So we're just saying that we can calculate the limit and get an answer. If the function is differentiable on an entire open interval, like at every point in there we can take a derivative, then we would say that it exists, the derivative exists on that interval, the whole thing. So if I draw you this piece of a function right there, does that appear that it would be differentiable on this entire interval? Yeah, there's no corners, no cusps, there's no jumps or breaks, there's no vertical tangents. So this should be differentiable everywhere here, right? Now remember us talking about continuity? What did it mean for something to be continuous? Continuous meant, yeah, you could basically draw it without picking up your pencil, right? This theorem, this is a theorem, it says that any function that's differentiable at a point has to be continuous at a point. So if I tell you right now that there's some function out there that you can calculate the derivative at 2, at x is 2, automatically you know that when you draw the function, right? If I tell you, hey, at 2, you can calculate the derivative exists, then you know that it's continuous there, which means that the function from the left and from the right go the same place and you fill in the hole in the middle. That's what the theorem says. If it's differentiable, it has to be continuous. I tell you, be careful. It does not say it the other way around. Just because you're continuous doesn't mean that you are differentiable. Can someone give me an example of a function that would be continuous? You can draw without picking up your pencil, but would fail to be differentiable? That straight line down wouldn't be a function. Like this wouldn't qualify as a function. So a function that you can draw without picking up your pencil, like an absolute value. Okay, great. So like that right there is continuous, yes? Draw without picking up my pencil, but it fails to be differentiable where? Right there, right? You have a corner, yes. A parabola is continuous, right? But it's also differentiable everywhere. Right? What I'm saying here is that if you're differentiable everywhere, you have to be continuous. I'm saying to you, be careful though. Just because you're continuous doesn't mean you have to be differentiable. Here's an example of a continuous function that's not differentiable. Now this is a continuous function that's differentiable. But just because you're continuous doesn't mean you have to be differentiable. All right? There's an analogy I like to use for this to help people understand, because this has to do with mathematical logic. All right. How do I want to do this? I won't get too much into it. Would you agree with this? If you live in Texas, you live in the United States. Do you agree with that? If you live in Texas, you live in the United States, at least unless we secede from, okay, but for now, okay, for now, if you're living in Texas, you're still living in the United States. Does that work the other way around? So if you live in the US, then you live in Texas. Right? It doesn't, you can't just flip it, right? And that's what I'm saying about that theorem, is that differentiability, if you're differentiable, then you must be continuous at that point. You cannot flip it and say that if you're continuous, you have to be differentiable. All right? So mathematicians were wondering for a long time, because mathematicians think this way, is it possible to come up with a function that you can draw without picking up your pencil, but you can never take the derivative anywhere on the function? So like here's an example of a function that I can draw without picking up my pencil, right? So that's continuous, isn't it, everywhere? If I just continue doing that, let's say you just continue this pattern both directions forever. Would you agree that that function is continuous everywhere? Now, is it differentiable everywhere? No. There's points at which it's not differentiable, right? Now, how about in here? Is it differentiable in here? Sure. Is it differentiable in here? Yeah, sure. So there's a certain number of points where it's not differentiable. Mathematicians said, is there a function that is continuous everywhere, but nowhere differentiable? Like you can never, like you go to any point on the function and there's no derivative. Can you imagine what it might look like? Al, you're shaking your head. Cube root? What does the cube root function look like? Something like this? Oh. So is that continuous everywhere? Okay. Is it differentiable everywhere? No. But there's only one point that it's not differentiable. Just right here, because you have vertical tangent, right? Okay, so this is an example of a function that is continuous everywhere and differentiable everywhere but one point. I'm saying, is there a function that's continuous everywhere and differentiable nowhere? See, this is still differentiable here and here, right? There's only one place it's not differentiable. I want a function that's nowhere differentiable. Yes?
Would that wouldn't be up, down, like vertical?
Yeah, we can't do a vertical line. because it's not a function. It fails the vertical line test, like, right? So that's not a function. Yes?
I was going to say a point, but that doesn't make sense.
Yeah, point. Let's say we would need, because I want it to be continuous everywhere, like on the entire real number line. So look, nobody's going to be able to tell me the function, okay? But I want you to think about what it would have to look like. And this is a good model for it.
You would have to have like holes on the slope.
It's got to be continuous though. Can't have holes. Right? I want continuous everywhere, differentiable nowhere.
Spiral.
Spiral wouldn't be a function, it would fail the vertical line test. So would you agree that one way we could do it is to make it look like that saw blade right there that we just had? But what we need is that when we draw it, we're good. We've covered these corners, right? We have no derivatives there. But we need that to happen all in here too, right? So imagine that this right here from here to here wasn't a straight line. Imagine that it was like a little saw blade like that. Okay? And then saw blade like that. And then when you zoom in on each saw tooth, right? So you zoom in that tooth has little teeth on it. And then you zoom in on that tooth, and that tooth has teeth on that. And you zoom in and infinitely zoom in. And so mathematicians were like, can we make that function happen? Can we actually create a function that draws this? And we did. It's called the Weierstrass function. So here it is. I'm gonna give you the sketch of it. This is it right here in a very generic form. This is it. What it basically is it's like a cosine function, okay? But within each of the cosines, they're corners. And so this is not the whole thing, but imagine that I made all of those little teeth have corners. So as you zoom in, let the computer catch up. As you try and zoom in on each corner has a corner, and each of those has little corners. So let me bring it up. I want you to see it, because you can just Google it. Because you probably want to know what the function is, right? Like what it is. I think I misspelled it. Who cares? Google is smart enough. There it is. That's kind of a better picture, I think. This picture right here, that's a picture of the Weierstrass function. Okay, it's like all these jaggedy edges, but I want the actual function. So there it is. It is the infinite summation of a bunch of cosine functions. And so to understand what this is, you have to take Cal 2, because Cal 2 we talk about these things. These are called infinite series. And so it is an infinite series of cosine functions that creates this drawing, and that is a function that is continuous everywhere and non-differentiable everywhere. Why is it continuous everywhere? Why do we know it's continuous everywhere? Because this is just the sum of a bunch of cosines, right? And we had a theorem a while back that said if you take two continuous functions and add them, they're continuous. So we know that when we add up an infinite number, we're still continuous. Proving it's not differentiable is hard, and I'm not going to get into that. But all right. Now, more notation. More notation. Since we can take the derivative of a function and get a new function, what stops us from taking the derivative of that function and then doing it again and again and again and again and again, right? So we have these things called higher order derivatives. So if you want to take what's called the first derivative of a function, that's just the derivative. That's what we were talking about, right? Just a little prime mark. That means take the derivative. We call that the first derivative. If we want to take the derivative of that answer, then we will use 2 primes. And therefore, this is called the second derivative. And what do we use for the third derivative? 3 primes. And then what do we use for the fourth? Well, we start to dump the the primes because it's going to get a little ridiculous after a while, right? So we put f with the little 4 here with the parenthesis around it. Now, be real careful here because there is a difference between somebody writing this and somebody writing this. So let's say somebody gave us this function x squared, okay? And then they said, all right, here's the function, f of x is x squared. What's this? This is that function raised to the 4th power. Okay, so this right here is x squared times x squared times x squared times x squared. This is, take the derivative of that, then take the derivative again, and then take derivative again, and then take derivative again. Four derivatives in a row. Make sense? So that parentheses is the indicator that it's a derivative. No parentheses just means it's a power. You're raising it. And once we get to this notation, well, how many derivatives can we take? 5th, 6th, so on forever. So you could theoretically take the 100th derivative of a function. Got it? So this is just notation. Now, when I was talking earlier about position, what was the first derivative of a position function? The first derivative of a position function gives you the velocity function, right? The second derivative of a position function gives you the acceleration function, right? Now, since we have 2 different notations, right, Newton's and Leibniz, how do we talk about higher order derivatives with Leibniz notation? So the first derivative is just dy dx. Okay, that's take the derivative. And then the second derivative is this weird thing. It's d with a little superscript 2y over dx squared, like that. That, if you ever see this notation, it means take the derivative twice. Why do you think they offset the 2's like this? Why do you think those are like that? Is that just to confuse you? Yeah, so you might accidentally think that that's this. Like this right here. That right there means what? Take the derivative once and then do what? Square the answer, right? Take the derivative once, square the answer. So most people would think that that is the same as this. Like this notation and this notation are the same thing. So in order to avoid any confusion about what those 2's are, we offset the 2's like this so that you understand we mean take the derivative 2 times. I hope that makes sense. And then what is it going to be for the third? 3's offset. 4th derivative, 4's offset them. 5th derivative, and so on and so forth. This last piece just summarizes what I already said. If you have a position function, the first derivative is the velocity, and if we take derivative again, we get the instantaneous acceleration. All right. So that section we're through. It's a lot of new notation and language, but there's your homework, as you'll see, is just going to be like you're going to look at some pictures and you're going to try and draw their derivatives, just like we did earlier. And there's some matching problems where they give you a function, they give you a bunch of functions, they give you a bunch of derivatives, the pictures, and you try and match them with each other. All right. We get to 2.3, one of my favorite sections. Okay. Y'all ready? No? You're not ready? Okay. Let's just kind of like clear everything off the table for, no, don't clear everything, but just mentally clear the table. Yes?
Is this all going to be on the test, like 2.3 and everything?
Oh, for the test, I don't think 2.3 will be there. This stuff, although when I'm done with it, you might want it there. Like it's actually the problems will be, you'll welcome it. Yeah. But we will say officially